Okay, these are going to be our notes about particle problems. So recall that if you're given a function that describes an object's position as a function of time, which a lot of times we will denote s of t. It doesn't have to be. It can be f of t. It can be any letter that you choose. But very often we'll use s of t. Then its instantaneous velocity, v of t, is given by v of t is equal to the first derivative of the position function. The object's acceleration as a function of time is given by the first derivative of the velocity, because acceleration is how velocity changes over time. But of course that's going to be as that time interval shrinks to be smaller and smaller and smaller. That's your acceleration. But since velocity is the first derivative of position, acceleration is then the second derivative of position. So part of looking at particle problems is going to be looking back at this relationship between position, velocity, and acceleration, as well as adding some new layers to that examination. Let's take a look. The position of a particle is given by the equation s of t equals t cubed minus 6t squared plus 9t, where t is measured in seconds and s is measured in meters. We're going to go through a series of questions about this specific particle. The first question is simply going to be, find the velocity at time t. And as we just discussed, velocity is the first derivative of the position function. So v of t, for this particular function, I was nice, I gave you a nice polynomial. It is going to be the derivative of t cubed, which is 3t squared, minus 12t plus 9. That's the derivative of your position function. That's the velocity at any time t. If we then want to know what is the velocity after 2 seconds or after 4 seconds, all we have to do to answer this is literally just plug in 2 seconds, because we're agreeing on the labels. You want to check the labels. T is supposed to be measured in seconds, and that's what I've given it to you in. If I had given it to you, I don't know, for some reason in minutes, you would have to convert the time to seconds to begin with. But we don't have to convert. So v of 2 is going to be 3 times 2 squared minus 12 times 2 plus 9. So that's 12 minus 24 for negative 12 plus 9 for negative 3. And then we need to get a label on that. Since it's velocity, which is a change in position divided by a change in time, your position is measured in meters and your time is measured in seconds. So that's negative 3 meters per second. And what the negative on this velocity is indicating is that if you're looking at how the position changes with respect to time, as that time is progressing on, your position is going to be decreasing, which we'll show in just a little bit when we look at a diagram of how this particle moves. So this question asks, when is the particle at rest? And what we want to keep in mind is that if our particle is at rest, that means it's not moving. And if it's not moving, that means its velocity has to be equal to what? Well, that tells us the velocity must be equal to 0. So if we want to know what's going to make our velocity equal to 0, we set it equal to 0. So from the previous slide, we knew that our velocity was 3t squared minus 12t plus 9, and we're going to set that equal to 0. I can factor out the 3. You don't have to. It just makes your numbers a little bit easier to deal with. Or you can just go straight to the factoring. This one does happen to factor to t minus 1 times t minus 3, but if it didn't factor, we could just use quadratic formula instead. So this tells me that my particle is at rest at 2 different times. It's at rest at 1 second, and it's at rest at 3 seconds. So the next question asks us, when is this particle moving forward? And by forward, we mean in a positive direction. Remember, if your velocity is positive, it's considered to be moving in a forward direction. And if it's negative, it's considered to be moving in a backward direction. So what this question is actually asking us is, when is v of t greater than 0? And that's strictly greater than, because if it were equal to 0, it wouldn't be moving. So what we're looking to do is to take our velocity, which I'm going to use the factored form of it, 3 times t minus 1 times t minus 3. And now we're not looking for where it's equal to 0, but where it's greater than 0. And this was a part of the pre-calculus review. You want to use test values to figure out where this is going to come out positive and where it's going to come out negative. Now, technically, time can't be negative, or I'd normally extend this to negative infinity and positive infinity. Since time can't be negative, you wouldn't have it to the left of 0. So we're going to check in between 0 and 1. I picked up 1 because that's where my particle rests. And then I'm going to check in between 1 and 3. And again, 3 ended up on this number line because that's where your particle's at rest. So in between 0 and 1, if I test a value, let's say x equals 1/2. Yeah, this is going to be my test value. 3 is positive. 1/2 minus 1 is negative. And 1/2 minus 3 is also negative. So I'm going to have a positive times a negative times a negative, which overall tells me that particular interval will be positive. If I plug in, let's say 2, 3 is positive, 2 minus 1 is positive, 2 minus 3 is negative. So that comes out negative. And if I plug in something like 4, that'll be a positive times a positive times a positive for positive overall. So we now know the behavior of the velocity for all times. Between 0 and 1 it's positive, between 1 and 3 it's negative, and from 3 on it will be positive. So we just need to answer this question, which is asking us for the positive directions. So this particle is moving forward between 0 and 1 and between 3 and infinity. And notice for most of these I have parentheses because again this is not or equal to 0. The one place I need to just give a quick look at is at t equals 0. Is this particle moving in a forward direction? Keep in mind most of these particles are not at rest when they begin. They're already moving. So if you notice, if you plug t equals 0 back into the non-factored form of our velocity, which was the 3t squared minus 12t plus 9, at a time of 0, the particle is traveling 9 meters per second. That is a positive velocity, and therefore it is traveling in a positive direction at exactly 0 seconds. So you include the 0 because it is moving at 0. You don't include the 1 and the 3 because at those times your particle is at rest. Okay, we want to draw a diagram to represent the motion of the particle. So what we want is a diagram that tells us where our particle is at any given time. So that means we won't be dealing with the derivative. We won't be dealing with the velocity function. If you want to know where your particle is at a given time, you should be looking at the position function, s of t, which is the position function that we began with. So if I start with a horizontal axis to describe where, so this is s, this is where my particle is. In order to find its starting position, we need to consider that to be a time of 0. So at a time of 0, when you plug 0 into our position function, in this particular case, our position ends up starting at 0. Now that will not always be the case. You can have a starting position of any number. This one happens to start out with 0. So what we know from the previous slide is that our particle between 0 seconds and 1 second is moving in a forward direction, is moving to the right. Between 1 second and 3 seconds, it's moving to the left, and from 3 seconds on, it's moving to the right again. So if I know that starting at 0 seconds, it starts at a position of 0 and starts to move towards the right, when does it stop moving towards the right? At 1 second. So the question is, where is it at 1 second? In order to answer that, we need to calculate s of 1 for our particular function. So s of 1 is 1 cubed, which is 1, minus 6, plus 9 times 1, which is 1. So after 1 second, this particle has gone to 4. It's at a position of 4 meters. So this is where my particle is located. It has started here, It started here at 0, and it has moved in this direction to 4. Okay. Now, that occurred at a time of 1 second. Okay. We now know that this particle is going to travel back to the left. We don't know where it's going to end up, but we know it's going to travel back to the left. The problem is if you just draw this diagram and draw right back on this line, and let's say your particle stops here, you're not going to be able to see it because you're retracing a path that you've already traced. So what we do is we give it an imaginary vertical change. There's no vertical change in the path of my particle, but we're moving it up so we can actually see where my particle is going to be located at a given time. So we know that this particle is going to travel to the left until a time of 3 seconds. The question is just where does it end up after those 3 seconds? So we're going to look for S of 3. Notice I'm not calculating S of 2 because I know this particle continues to travel to the left until it stops at a time of 3. So when I plug in 3, we get 3 cubed, which is 27, minus 6 times 3 squared, so that'll be 54, plus 9 times 3, which is 27. So it turns out my position at time 3 seconds goes back to 0. So it goes to here. It goes back to a position of 0, and that's at a time of 3. So it's traveling this way between these two times and this way in between these two times. Notice, because this is not a linear function, it only took the particle 1 second to move from 0 to 4, and then it took 2 seconds for it to get from 4 back to 0. So these are not linear. And then according to the part D that we just completed, we know that after 3 seconds, our particle moves to the right and continues to move to the right. So again, I gave it a false vertical change just so that we can see the path that our particle is taking. So that's the diagram for the motion of the particle. The next question is going to ask us to find the total distance traveled by the particle during the first 5 seconds. And before we actually go about doing that, I want you to take a look at something. Pretend I had a particle on the left side of this screen, and I am going to cause this particle to move. But what I want you to do is I want you to close your eyes while I count to 5. And I just want you to know where the particle is when you close your eyes, wait the 5 seconds, and then open your eyes and note where the particle is. So here's the particle. Close your eyes. Yes, close them. Keep them closed. 1, 2, 3, 4, 5. Now open your eyes, and I want you to observe the particle's new location. How far does it appear to you that this particle has traveled if you had your eyes closed? Well, according to the units I have drawn on here, it would have traveled a total of 10 units. But in reality, if you watch it again, I'll replay it. Here it is. 1, 2, 3, 4, 5. Now notice this particle, while you had your eyes closed, actually went back and forth a couple of times. The total distance traveled of this particle was actually 30 units. So when we ask you to find the total distance traveled by the particle, you cannot just look at the beginning time, which in this case will be 0 seconds, and the end time, which is 5 seconds. You have to examine everything going on in between. And if you look at the diagram above this question, you've already got it kind of mapped out. You know this particle goes back and forth. So we have to take all of that traveling into account. So we know that in between a time of 0 and 4, this particle traveled a total of 4 meters. Now, just to give you the math notation on how we did that, we took the position at a time of 0. We knew that our particle stopped at a time of 1 second, and what we needed to know is where was it when it stopped. So we looked at S of 1. On the off chance that this came out negative, we need to look at that inside absolute values. We calculated S of 0 to be 0, and we calculated S of 1 to be 4. And sure enough, that ended up coming out negative just because of the order I went in. But once you take its absolute value, it turns out that between 0 seconds and 1 second, our particle traveled 4 meters. That's what we saw up above. Again, in between 1 and 3 seconds, we already know the answer is going to come out to be 4 in between 1 second and 3 seconds. But the notation would be s of 1 minus s of 3. Inside absolute values, we knew that s of 1 was 4 and that s of 3 was 0. And that's how we got 4 meters. Now we actually have one more piece to take into consideration. This is only how far it's traveled for the first 3 seconds. We need to look at the first 5. So then what we need to do is look at the position of the function at 3 seconds in comparison to the position of the function at 5 seconds inside absolute values so that we make sure that the distance comes out positive. We already know s of 3, it's 0. S of 5 is one more calculation we need to do really quickly. So s of 5 is 5 cubed, which is 125, minus 6 times 25, which is going to be 150, plus 9 times 5, which is 45. So s of 5 is 20. So we have the absolute value of 0 minus 20. So the distance traveled between 3 seconds and 5 seconds was 20 meters. So in total, the distance traveled by the particle between 0 seconds and 5 seconds is a total of 28 meters. The next question is going to ask the displacement for the first 5 seconds. And just in case you don't know what we mean by displacement, that is the change in its position for the first 5 seconds. Do you remember what the particle looked like when you did close your eyes? That's displacement. Displacement is the final position minus the initial position. Okay, so the good news is we've actually done all of the calculations for this on the previous slide. The final position is its position at 5 seconds, which we determined to be 20, minus its initial position, which we determined to be 0. So the final position of 5 at 5 seconds, this is s of 5 minus s of 0. That's 20 minus 0, and it turns out it's 20 meters. So let's have a conversation really quickly about whether or not total distance traveled can be positive or negative, and whether displacement can be positive or negative. When we talk about the total distance traveled, distance by definition needs to stay positive. That's why you saw a lot of absolute values going on in there. Even if your particle travels, say, 5 meters to the left, it's still a distance of 5 meters. So we take the absolute value when we're talking about the distance or the total distance. The displacement, however, is just the difference in the final position compared to the initial position. That can absolutely come out negative. If you have a particle that begins at a position of 0 and after 5 seconds ends up to the left by 10 meters, inches, whatever, then its displacement is negative 10. All that indicates is it is 10 away from its initial position, but the negative indicates that it ended up to the left of its initial position, assuming that you would choose left to be the negative direction. The next question we're going to look at is find the acceleration at time t and after 4 seconds. And as we mentioned, acceleration is just the derivative of the velocity. So if you recall, our velocity function was 3t squared minus 12t plus 9. So our acceleration will be given by its derivative. So that's going to be 6t minus 12. And then the acceleration after 4 seconds is a of 4. And that's 6 times 4 minus 12. So that's 24 minus 12. It's 12. Now that's meters per second squared. Okay, don't forget that your acceleration will be your position measurement divided by your time measurement squared. Then we're going to ask you to graph the position, velocity, and acceleration functions for 0 less than or equal to t less than or equal to 5. So these are the three functions. The position function that we started with, its first derivative for velocity, and its second derivative for acceleration. And I've gone ahead and put those into a graphing calculator to take a look at. You should know how to graph these kinds of functions by hand, but for the sake of speed, I'm going to go ahead and put them in the graphing calculator. So the reason we want to do this is keep an eye on the relationship between the graph of a function and the graph of its derivative. So the original position function was our cubic. That is this one. That's our red function. And notice when you start to talk about its derivative, if you start examining the slope of its tangent lines, we expect them to be positive, 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 and then 0. And sure enough, the velocity function has a 0 as soon as the position function has a horizontal tangent line. And you can find a similar relationship between the velocity and the acceleration. Notice at the beginning of the time at t equals 0, the slope of the tangent lines to the velocity function are negative, 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 and then right about here they pick up a horizontal tangent line. And note the acceleration, which was our linear function. It's negative, and then right here it picks up a 0, and then it turns positive. So those relationships that we discussed between graphs of functions and graphs of their derivatives hold true for the position, velocity, and acceleration functions as well. Then we want to talk about when is our particle speeding up and when is it slowing down. So we know that probably has something to do with acceleration. And let me remind you, our acceleration function, our second derivative, was a of t equals 6t minus 12. And you may suspect that speeding up and slowing down have to do with when your acceleration is positive and when your acceleration is negative. And that would make you partially correct. So let's go ahead and figure out when our acceleration is positive and negative. This is linear, so it's more straightforward than our velocity. We're literally just going to take 6t minus 12 and say when is that greater than 0? That's of course when our acceleration will be positive. And because it's linear, you can just add the 12 and divide by 6. So t greater than 2. So we expect acceleration to be positive when t is greater than 2, and we expect acceleration to be negative when you kind of want to say when t is less than 2, but be careful, t can't be negative because it represents time. So when t is in between 0 and 2. Do notice though that if t equals 0, your acceleration is also negative. So that one actually gets included. If you try to plug in 2, your acceleration is no longer negative. Now your acceleration is equal to 0. So that's why the 0 is going to be included, but the 2 is not. What we need to be careful of is assuming that, oh, if acceleration is positive, my particle is speeding up, and if acceleration is negative, my particle is slowing down. That's only half the story. That is true if your particle is already moving in a positive direction, but that's not true if your particle is moving in a negative direction. Let me show you what I mean. If you have a particle that is moving towards the right, and let's assume the right is your positive direction, and you have acceleration acting on it in the positive direction, meaning acceleration is positive. So velocity is positive, acceleration is positive. That is definitely going to speed up your particle. If your particle is moving to the right and acceleration acts on it in a negative direction, pushes it towards the left, your particle is then going to slow down. But what if your particle is moving already towards the left? That would indicate that your velocity is negative. If your acceleration then acts on that particle in a positive direction, they are now opposing each other. Your particle in this case will slow down. Likewise, if your particle is moving to the left, meaning its velocity is negative, and your acceleration acts on it in a negative direction, meaning your acceleration is negative, that will actually speed up your particle. So the moral of the story is, if you want to talk about when a particle is speeding up and when it is slowing down, you need to examine both the sign of the acceleration and the sign of the velocity. So if you can remember and juggle the signs of your velocity and acceleration at all times, that's great. I usually put them on just a little bit of a chart to help me remember what's going on. So this is time. This is not the same thing as that particle motion chart. This is a time. And I look at between 0 and 1, 1 and 2, 2 and 3, and then so forth. The reason I'm choosing these numbers is because I know that my velocity was equal to 0 at 1 and at 3. So my particle was at rest at 1 and at 3. The reason I included 2 is because my acceleration is switching from positive to negative at 2. So if you remember, for velocity, I'm just recapping what we had already done. Between 0 and 1 second, our velocity was positive. Then between 1 and 3 seconds, our velocity was negative. And then from 3 on, our velocity stayed positive. Acceleration, we have right here on this screen. The acceleration is negative for all times between 0 and 2. And then it's positive for all times beyond 2. So what I notice is the following. The signs of my acceleration and velocity are different between 0 seconds and 1 second, and 2 seconds and 3 seconds. In those time intervals, I expect my particle to be slowing down. However, between 1 second and 2 seconds, and then again from honestly 3 seconds on, the signs of velocity and acceleration are the same. They agree. So in those time intervals, I expect my particle to be speeding up. So let's write that down. My particle is slowing down from 0 to 1 and 2 to 3. Again, we don't include the 1, 2, and 3 because your particle is at rest at 1 and at 3, and at 2 it's switching signs on its acceleration. However, we are going to end up including 0 because it ended up being included in both the negative acceleration and the positive velocity. So 0 gets included on this one. And then I expect my particle to speed up in between 1 second and 2 seconds, and again from 3 to infinity. So that's speeding up and slowing down. So that's the essence of particle problems. It is, on its basic level, talking about the fact that if you have a position function, its first derivative is velocity and its second derivative is acceleration. But there's a lot of other information that you can pull out of those relationships, and that's what particle problems are all about.